Okay, questions over homework? Any questions? Did y'all try the implicit differentiation? Did y'all get started on that? How'd it go? Come on. No questions? Yeah, my book is actually in my office still. Can I borrow yours?
Sure.
9x squared plus y squared equals 9. You asked to find y double prime?
Yes.
All right. Well, it would be rather difficult to solve for y explicitly here, because if you try and solve for y, you eventually have to take a square root. So you get plus or minus, and that would become an issue. So this is perfectly suited for implicit differentiation, since you have the equation sitting there. So let's go ahead and do that. I might be receiving a phone call or a text message, and just so you know, if I do get a phone call, I'll walk out of the room, as I would expect you to do. I won't just start talking on my phone. But just a heads up that may happen. All right, so I'm going to do implicit differentiation. So that's what I did last time to let you know I'm about to do implicit differentiation. And I'm going to be taking the derivative with respect to what variable? Derivative of y with respect to x. So I'm going to treat x as the independent variable here. So we're going to act like y depends on x. So what is the derivative of 9x squared in that case? Just 18x. Then we can say dx, but I hope that you've all come to the point where we're OK with that. All right. And then this one, 2y dy dx or y prime. Are we comfortable to do that now instead of dy dx? OK, on the right side of the equation, 0. And we're trying to solve for y double prime. So let me show you one approach, and I'll show you another approach after I finish. One approach would be at this point to solve for y prime, if possible. So I'm going to take the 18x to the other side, get 2y y prime equals negative 18x. Divide both sides by 2y to get y prime equals what? Negative 9x over y. Okay. And then at this point, I could do implicit differentiation again. So what is the derivative of y prime with respect to x? Y double prime. And then on the right side, what are you going to have to do? Quotient rule. Right? Quotient rule. So it'll be the derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. The top is negative 9x. The bottom is y. So that's just filling in what the quotient rule is going to be, right? I haven't taken any derivatives yet. When I actually take the derivatives, the derivative of negative 9x with respect to x is just negative 9, and then times y, and then minus. Now here's where you have to be a little careful here. What's the derivative of y?
Wouldn't the bottom be just y squared?
Why did I put that? Y squared, yeah. Sorry about that.
Isn't it just dy dx?
Yeah, the derivative of y is dy dx, or just y prime. So we have y prime right here, times negative 9x, right? All over y squared. Any questions on that? That is the second derivative. That is it. But the y prime in here is a little bit, you want your answer to have x's and y's in it, but you don't want it to have y prime in it, if possible. Yes? Yeah, you just, whatever we said y prime was, let's just plug it in right there. And then we're going to try and simplify it to get it to look like whatever the book says. So y double prime equals negative 9y minus y prime, which we said was negative 9x over y, but that's times negative 9x again, and then all of that over y squared.
So now you can just do a common denominator?
We'll do a common denominator here in just a second. I'm going to put these two together. So that's really like a negative 9x over 1 multiply across. So you get what, 81x squared over y? But it's subtracted. Two negatives is a positive. So this should be minus 81x squared over y all over y squared. Now, I heard common denominator. That would be okay. Yeah, let's just do that. Common denominator between these two? So that's over 1. So you have to introduce a y down here and up here. Multiply it. So you get negative 9y squared, right? That's this. Then minus 81x squared over y over y squared. And you can look at that y squared on the bottom as being like y squared over 1, and then flipping like this. So what will that turn into? A y cubed on the bottom. And everything on top is still the same. So we get that this equals negative 9y squared minus 81x squared over y cubed. And that is what I would say is the second derivative. It doesn't have the y prime in it. It's pretty clean. I do want to go back and take a look. The original problem was y equals 9x squared plus y squared. Or sorry, was that the original problem?
Yeah.
Right. What's the answer in the back? Is it this, or is it all in terms of x?
It's negative 81 over y cubed.
Negative 81 over y cubed. Okay, so let's see how they got that. Look, anywhere you see you can, they have it in terms of x or y? You said negative 81 over y cubed?
Mm-hmm.
So that means they don't have any x's in their answer, right? So can you tell me what x squared is? So can you solve that for x squared?
It's 2x.
What's x squared? 9x squared equals 9 minus y squared? Yes?
It'd be plus or minus the square root of 9y squared.
Yeah, you're solving all the way for x squared, right? Let me try something a little different. It might help. How about this? I'm just trying to match the back of the book, right? Okay, this equals, let me pull out a negative 9 from these two, all right? Pull a negative 9 out, and what would you be left with?
Y squared minus.
Y squared
Plus 9.
plus 9x squared. There we go. That'll work better over y cubed. I was going to try and just divide through by 9 here. It was going to create a fraction. I didn't like that. So instead, realize I pull a 9 out, and look at this. What's this? What's this? What's 9x squared plus y squared equal to? 9. So 9x squared plus y squared is 9, isn't it? This whole thing is 9, according to the original equation.
Yeah.
So negative 9 times 9 is
Negative
negative 81 over y cubed. So even though this is an appropriate answer, this answer, for you to know the derivative, you actually need to know the x coordinate and the y coordinate of the point, right? But according to this simplification, to know the derivative, all you really need to know is the y coordinate, and you know what the derivative is. Interesting. Questions? Does anybody know what that curve is? The original problem?
Isn't it a circle?
Almost like a circle. Oval, ellipse,
Yeah.
ellipse. Let's see. What would happen if I let y be 0? What would I get? X would be, if y is 0, you have 9x squared equals 9.
So 9 minus.
So x squared equals 1. So x is what? Plus or minus 1? So that would be like 1 here. So it could be here or here. Y is 0, x is positive or negative 1. What if x is 0? Then y is plus or minus 3, so that's this. And then if you put it together, you'd have to fill the other points in. But you would need to recognize that that's an ellipse to know that that's the shape. But so what this is saying, according to this, is that if I want to know the second derivative, not the first derivative, I want to know the second derivative, which is not the slope of the tangent line, is it?
No.
The second derivative, all I need to know is the y-coordinate. Give me the y-coordinate of this point, I can tell you what the second derivative is. First derivative would represent the slope of the tangent line. Yes?
Is there a function where there won't be like, where there only is a set amount of derivatives, where you can't keep going after the first derivative?
Well, if you look at like a polynomial function, like take like x squared. The first derivative of x squared is 2x. The second derivative of x squared is 2. The third derivative is 0. Fourth derivative is 0. Fifth derivative is 0. Sixth derivative is 0. So you do have functions that eventually they go down to 0, and then every derivative after that's just 0. And then sometimes you have functions that repeat, like you have like derivative of sine is cosine, derivative of cosine is negative sine, derivative of negative sine is negative cosine, derivative of negative cosine is positive sine, and then you're back to sine. So then it's just going to repeat. Every 4 derivatives, it'll just repeat. Does that make sense? Then you have derivatives where you take them and it gets more complicated. Second derivative gets more complicated. Third derivative gets more complicated, and then it just gets out of hand. So there's functions in all different categories. Does that make sense? Like some get better, some get worse, some cycle. Any other questions on the homework? I got an email saying that the projector in this room is all messed up and that it's going to be 2 weeks or something like that before they get it fixed. I don't know what the deal is. But the section that we're going to cover today, related rates, it would be really nice to be able to show you some of the animations that I have for this section. So, you know, in the beginning I was asking you to go watch those course videos. I would recommend that you do go watch the course videos for wrong chapter, sorry. What is it, 3.6? No, 2.6.
That's where we're at now.
Yeah, I'm in the wrong chapters. 2.7. Okay, we're pretty much done with implicit differentiation. We're going to talk about related rates now. So please watch the section on 2.7 course video. I think it's kind of long because there's a lot of stuff I talk about. Some of these videos are really short, like chain rule and product rule, very short. This one, there's a lot of examples. I think, let's see, there's 17 notes. There's probably about 10 to 12 examples in here. So, yeah, watch that. But I'm going to go through it today. It's just I won't have the nice pictures to go with it, the nice animations. So usually when I talk to Cal 1 students or I talk to Cal 2 students about Cal 1, and I ask them, you know, what parts of Cal 1 gave them problems, a lot of them talk about related rates as being one of those sections that they just never really got their heads around. And that's very common, all right, because this is going to be word problems, and there's going to be a procedure that we're going to try and follow, but in general, every problem is unique, it's different, and so it's not as cookie cutter as like product rule. There's only one product rule, right? I mean, there's only one way to do it. Yeah, the algebra can get ugly, and sometimes the derivatives get messy, but you know, product rule is just, you just do it, right? Quotient rule, you just do it. Chain rule, you just do it. So with the related rates, if you feel like, what in the world's going on, that's pretty normal to feel that way. The only way that you actually get better at it, though, is to continue to do more and more and more problems, just like anything else in math, right? So what is related rates? I kind of alluded to this a while back, last class. I showed you that equation, right? We talked about how the beauty of implicit differentiation is that you can take any equation that exists, and you can find how the rate that one quantity changes is affected by the rate that the others change. So like if temperature changes a little bit, how does that affect pressure, right? If I change temperature, pressure is going to change. And what we're interested in calculus 1, what we're interested in is finding rates of change at instants in time, which goes back to the motivation for the tangent line. When I first started talking about tangent line, I said, look, let's say we have like time, and let's say we have distance. Then if you connect a curve in here, that the slope of this line would give you an average speed over the entire trip, as opposed to the slope of a tangent line, which would give you the speed at the instant in time. And we said, okay, but that's going to cause 0 over 0, and then we got around it with the limit, right? This is the same exact thing. We are trying to find instantaneous rates of change in quantities, but now we're going to move away from the velocity, and we're just going to look at just arbitrary things. Like it could be that, but that's not where we'll start. Okay, we're going to start with an example with a circle, because everyone's pretty familiar with a circle. So let's say we have a circle. Let's say it has a radius of r. Let's talk about the things that we know about circles, all right? We know that the area of a circle is pi r squared, right? What other things do you know about a circle? Diameter, I'll say little d, is twice the radius. You could also say that the radius is half of the diameter, right? What other things do you know about circles? Circumference, the circumference, capital C, is 2 pi r. But what's 2r? What's 2 times r? Is the diameter. So you also have a formula that says pi d, right? That's not as well known, right? But it's the same thing. So these are all just the general things we know about circles. Yes? If I fix a radius for you, you can give me all that information, can't you? All right. So let's look at some specific examples. If r is 2, or let's start with 1. If r is 1, let's list out some things we know. What's the area of the circle? Pi, right? The area would be pi? Okay. What would the diameter be? 2. Of course, the radius we already know is 1, because I told you that. And then the circumference would be what? 2 pi, right? 2 pi. I'm just taking all these equations and plugging in r as 1. Right? That's what we get. There's no magic here. This is just plugging numbers in, right? All right, let me change the radius for you. Okay, what I'm going to do is imagine that I take that circle that had a radius of 1. I'd like to increase the radius by 1 now. So it's at 1 right now. I'm going to increase it by 1. So what's the radius going to be now? The radius is going to be 2. So if the radius is 2, give me the information again. Area would now be what? 4 pi. What would the diameter be? 4. What would the, well, radius we already know is 2. What would the circumference be?
4 pi.
4.
8 pi.
My radius is what? 4 pi? Sorry, my radius is 2, so it would be 4 pi? Do we agree? So let's just see what happened here. I increased the radius by 1 unit, right? How did the area increase? The area increased by 4, didn't it? By 4-fold? Yeah? The diameter, what? Doubled. The radius doubled. Circumference doubled, right? So everything seemed to double, but the area didn't. The area didn't double, did it? It went up by 4, by a factor of 4. Let's go one more. Let's jump that radius up again to 3. If the radius is 3, what's the area? 9 pi. Diameter, 6r, 6, right? R is 3. Circumference would be 6 pi. Let's focus just on area. At 1, we had pi. At 2, it went up by a factor of 4, didn't it? Went up to 4 pi. And when I jumped up one more increment, did it go up by 4 pi again? It didn't. Did it? It went up by 5 pi's? Well, let's see. Do y'all kind of get it, what I'm saying? You could say that if I multiply pi by 4, I get 4 pi. But in terms of pi's, how many more pi's do I add on this to get 4 pi? 3 of them? So I added 3 pi's to get 4 pi's. To get from here to here, how many pi's did I have to add? 5 pi's. What I'm trying to get you to see is that the relationship doesn't seem to be linear, like the relationship with circumference. Look at circumference. 2 pi, on the next step up, it became 4 pi, so I added 2. The next step up became 6, so I added 2. So it makes sense that each time I step up, the circumference keeps increasing by the same amount. Yeah? But it's not working that way with area. Maybe one more. If r is 4, what's my area? 16 pi. And then these, how about circumference? 8 pi? Is it 8? Right? 8 pi? So did the circumference follow the pattern? It just keeps like going up by 2 each time? But the area, again, is not going up by the same amount each time. And that's because the area formula has a squared in it, whereas the circumference formula does not. So what we're interested in this class is not what's happening at these exact moments. You know, like we have this radius that's fixed and I ask you what the area is. That wouldn't be a calculus question, would it? Right? It wouldn't. So what we're doing here instead is this. Imagine having a circle where maybe we can look at it like like I'm pouring out a bucket of paint onto the ground. And as the paint hits the ground, it forms this puddle, and this puddle is a perfect circle, let's say. And that circle is growing on the ground, right? So we start out with this circle, and the radius is growing at a constant rate. So imagine I'm pouring out the paint in such a way that after 1 second, let's say the radius was 1. 1 second later, the radius is 2. 1 second later, the radius is 3. 1 second later, the radius is 4. So the way that the radius is growing is constant. Do you all understand that? The question is, how fast is the area changing? We know the radius is changing at a constant rate. How fast is the area changing? Understand?
You mean like time?
it's a rate, so it will be like speed is, miles per hour. It'll be something like that, but it won't be, how do we measure area of something? What's that? It seemed like it was going up by odd numbers, right? So
You have to do like centimeters
squared. If the units were centimeters, it would be centimeters squared per second, per minute, per hour, whatever it is. What I'm trying to get you to see to start this, though, is that if I say that the circle has a certain radius, and I say it changes by, let's say, 1 increment, if I just tell you that, it changed by 1 increment, does the area change the same as it would change at a different increment of time? No. So don't you also have to know what the radius is to be able to answer that question? Because in the beginning, we saw it was going up, like initially it went up by what, 3 pi's, and then the next time it was 4 pi's, and the next time it was 5 pi's. So in order for you to tell me how fast the area is growing, you actually need to know what the radius is to start. I could be confusing this or making this more complicated than it has to be here. So let's just first make sure we understand the picture. That's a circle, it's growing, the radius is growing at a constant rate. Got it? The rate, the radius is growing is, I'm going to make this up, 2 feet per minute. 2 feet per minute. So we're pouring this very slow, all right? The paint's going, and then it's growing, and that radius is growing 2 feet. Every minute, the radius grows by 2 more feet, and it's doing it at a constant rate. What I would like for us to do is find the rate, the area is changing when the radius is 8 feet. I'm going to try and draw another picture here just to get you to understand what's happening. If I draw a circle right now that has a radius of 1 foot, 1 minute later, what will the radius be? 3 feet, right? So that would be 1, 2. So now this is the circle. That's the circle now, right? Something like that? How much area did we gain in this? In that 1 minute, how much area was gained? Everything here, right? Yes? Now, let me draw a circle with a radius of 8 feet. So that's 3. So let's say that's 6. Let's say that's 8. Something like this. Circle with radius 8. Right? There's a circle with radius 8. After 1 minute, what's the radius? 10. So now my circle is like this, right? How much area did I gain? Everything out here, right? So in which scenario did I gain more area? Here or here? Is it? I mean, look at it geometrically. Is this area right here the same as the area of that band that goes all the way around that 8-foot circle? Which one's more? The big one, right? So that's what I was trying to get at, is that if I give you a circle, I don't tell you what the radius is, and I tell you to tell me how much that area is changing by, you need to know how big that circle was. And the bigger the circle is, the more area I get as I go out, right? If I start with a small circle, I change it by this much, an inch or 2 inches, I gain some area. But if that circle was the size of this room and I change it by 1 inch, look at that huge area it gains in that one inch. Yeah? Okay. Okay, so there's a question. Everyone has that question down, written down? All right, so what is the procedure? I have the procedure listed out in the notes, all right? I'm just going to write it down. What I recommend you do, all right, in all these problems is draw two pictures of what's happening. Okay, you're going to have one picture, which we'll call the general picture, and then another picture, which we'll call the instant in time picture. And then what we'll do is we'll draw both pictures and we will actually label them with variables and whatever we know, whatever constants we know we'll put in there. The general picture is a circle. And that circle is growing, right? That circle has a radius. And in general, the radius is r. I know in the instant in time that I'm talking about, the radius is what? 8, right? But that's this picture, not that picture. This general picture, the circle is changing, right? As time goes on, this puddle is growing. So that's my general picture. Over here, I can actually fix the radius to be 8, what, feet? And then somewhere on the side, we're going to write down all the information from the word problem. We're going to write down what we're given and what we want and when we want it. This is the format that I will use for all of these problems. I'll draw a general picture. I'll draw an instant picture. I'll write down what I'm given. I'll write down what I want. All right? That's what I'm going to do. What am I given? The radius, right? I'm given the radius. But that radius is at that instant in time, isn't it? Okay. So I agree. We are given radius. But I'm not going to put in my given yet. What's the other piece of information?
Growing at 2 feet per minute.
What's growing?
The radius is growing.
The radius is growing at
2 feet.
2 feet per minute. The radius is growing at 2 feet per minute. Okay, radius is a measurement of a distance, right? A length. And per minute means time. Yes? So when we say, I don't want to put it right here, I'm just going to write down 2 feet per minute. I'm really saying 2 feet per 1 minute. That's what that is. It's a ratio. And that tells me the rate that the radius is changing, right? That gives me the change in the radius. Isn't the rate of change of something the derivative? Like when you talk about rate of change, slope of a line is rate of change, but at an instant in time. So could I say that dr, the change in radius, with respect to time, t, is equal to 2 feet per minute? Would that make sense to you if I wrote that down? The change in radius with respect to time is 2 feet per minute. Feet is a measurement of radius. Minutes is the measurement of time. That makes sense? Okay. If that's what I'm given in the problem, what is it that I want to find?
At 8 feet, what is
At exactly 8 feet, what is what?
the radius?
Nope. Read through it. The rate that the area is changing, right? I'm not saying, hey, look, everyone, see this circle? What's its area? That's not a calculus question. Everyone can do pi r squared. The calculus question is, at exactly the moment that that puddle is 8 feet, at that exact moment, how rapidly is the area increasing? Not what's the area, how much is it changing? So I want the the area changes, right? So rate means derivative to us. I want the rate that the area is changing with respect to time again, right? With respect to time. This already dictates what it's going to be with respect to. What was given to me, everything's going to be with respect to time. So I want to know the rate at which the area is changing with respect to time. That's what I want, right? When do I want that? At 8 feet. At what's 8 feet? When the radius is 8 feet. When r equals 8. So I've written down what I'm given. I've written down what I want. Is there any other information in the problem that I've left out here? I've taken care of all the numbers, right? I've got the 8 there, I've got the 2 there. I've got what I'm trying to find. So everything is here? All right. We're about to do the problem, but I just want to make sure everyone has their head around what's going on. If I'm standing here, right, and I say right now, how fast am I moving? What's my speed? What would you say? Relative to the ground, it would be 0, right? Yes?
Yeah.
Because I'm not moving. So if I look at this circle right here at 8 feet, and I fix it at 8 feet, and I say, how fast is the area changing? What would you say? It's not. Why are you asking me that stupid question? This is not changing, right? So if I want to know how fast the area is changing with respect to time, I'm not allowed to freeze that in time. I have to allow it to change. So that means if I'm sitting here actually walking across the room and I say right there, when I clapped, how fast was I going? See, I didn't actually stop moving. And so what you need to remember is that once you get your information down, you're going to need to do some derivatives. You cannot fix this to be 8. Because if you do, your answer is going to not make any sense. Because what's the derivative of 8? What's the derivative of a constant? 0. So you're going to tell me you're not moving, right? So all derivatives must be taken before you fix any constants in the problem. This value right here, you can't fix it yet. All right. So we have general picture, instant in time, what we're given, what we want, when we want it. Your next goal is to look at what you're given and identify the variable here, and then what you want, the variable here, and then come up with any equation that exists in the universe that connects this to this.
So A equals pi r squared.
Any equation. In fact, this is radius, right? Radius of the circle. This is area of the circle. Any equation that relates area of a circle to the radius would be pi r squared, right? So you write that equation down now. Area equals pi r squared. So we found equation, right, relating R and A. Area equals pi r squared. And do you see what I'm trying to get at now is that formula from last class. I tried to convince you that it doesn't matter what equation you're ever given. You can always come up with the relationship between those variables if you can take the derivative of it, right? If you take derivative, you have connections. So what I've done is I've created an equation, right, using the formula of the area of a circle that contains the two variables I know something about and that I want to know something about. And now I'm going to differentiate that. And I'm going to use implicit differentiation from last class. But this time I'm going to actually differentiate with respect to what variable? T, which doesn't appear in my equation, but it's that third background variable of time, right? So what is the derivative of A with respect to T? dA dt. It's exactly the derivative of A with respect to T. Am I happy to see this?
Yes.
Absolutely, because that's what I actually want to find, don't I? All right, equals. Now pi is a constant attached to a function. So it's just going to come along. What is the derivative of r squared? 2r. 2r times dr dt. That's chain rule, right? 2 comes down, r to the first power. dr dt is the derivative of what's down here. And are we happy to see that?
Yeah.
We are happy to see that. And, what did you say? And we know R, don't we? We know R at the instant. Now, do you see again now why I could not replace that with 8 up here? Because if I did that, this would be 64 pi. And then you would take the derivative of 64 pi and get what? 0. So what you're doing is you're asking the question too soon. You're actually freezing the circle and then saying, how fast is it moving? Instead of letting it move and then saying, right then, how fast was it moving? It's subtle, but it's so important. You can't differentiate too soon. So now this, I mean, we have it. This is it. That's it. You just have to plug things in now. So what's dA dt? Well, that's what we want to know. Pi we know is pi. 2 is 2. And now replace r with 8. And then replace dr dt with 2, right? So I have this. Well, let's talk about that. dA dt will be equal to, hey, I forgot to show you the other way of doing that other problem out of the homework. Remember I said I was going to show it to you both ways? I forgot, sorry. Pi times 2 times 8 times 2. So pi times 2 times 8 times 2. 32 pi is dA dt. Now, that's the way I do it. I've always done it this way. And I haven't kept track of the units until the end. I'm going to show you both ways. Don't let me forget. The reason why I don't keep track of units is this. I know that this answer is a rate, don't I? I know it's the rate of area over time. How would you measure area in this problem? Well, what's your unit? Feet? So square feet? So this would be feet squared per, what's your measurement of time? Minutes. So 32 pi square feet per minute. Now, if you prefer to keep your units there the whole time, you get the same answer. You would go pi times 2 times, now what was the 8? The 8 was 8 feet. Sorry, 8 feet times, now what was the dr dt? 2 feet per minute. So let's write 2 feet over 1 minute. And then when you multiply these together, you get 32 pi, and then feet is feet squared, and then over 1 minute would be minutes, right? So it's up to you. If you take a physics class, they usually want you to keep your units in there. With this, you can always tell what the answer is going to be because of these two things right here. As long as you know that area is measured in squared units and volume is cubed units, right? Let me check this. I asked for them to call me, and they decided not to call me, so. I get 10 points taken off my next test. What do y'all think?
This
Not
one's
bad.
pretty easy.
I think they're all not going to be like that.
Yeah, this is the first example, so we start. What I want you to see, the more important thing for me is for you to understand what this quantity represents. You know, you've got this circle. It's got a radius of 8 feet, but that circle is growing, right? I'm going to turn this off. Or silence it. Silence!
What happens if they call you?
I know. Well, it looks like everything's okay. They're sending pictures back and forth, so. Okay, I'm on a group thing, you know, those stupid group things. All right, so this number right here, this quantity, is that if I were to let this thing increase infinitesimally, which means at the next little infinitesimal moment of time, this circle is going to grow by just an infinitesimal amount, right? Just a little bit, right? Just a little bit. And that red area is 32 pi. What I'm not saying is what the area is 1 minute later. 1 minute later, it grows by 2 feet, right? I'm saying at that instant, exactly that instant in time, it was moving. And if it just moved on an infinitesimally small increment of time, then that area would change by 32 pi. It's, believe it or not, it's the same question we were saying with velocity. If someone's running and you're trying to find their speed at an instant, right? The way we got around that is we said what? We did a limit, right? We said, look, we can't talk about, if we take a curve, it's very easy for us to find the slope between these 2 points, but that's an average speed. That would be like the 8-foot circle and then the 10-foot circle a minute later. The way that we actually find the speed at that point is to slide this point along here, right? And get it how close? Infinitesimally close. In fact, we let it approach the same thing, and then we get a numerical value for that slope. Same exact concept. We have the circle. We know the radius is 8. We know a minute later it would be 10. But what we do is we bring that in, and we let it get infinitesimally close. But we can't let it be 8 because then the circle's not changing, right? It's kind of the same idea. All right. I realize with an example like this, it's very difficult to understand why you'd ever want to do anything like this, right? Like, why would you even want to know that quantity? I'll give you a quick example of something you would want to know. Let's say you have a transmission, right? So I don't know if people know about engines, but you've got pistons in your engine, right? These pistons are attached to, what are these called? The rods that go down to the crankshaft. And the crankshaft, so the pistons are going up and down because of explosions, and then this is turning, right? And that interacts with the transmission, and there's a bunch of gears, and at the end you go to your drivetrain, and that turns eventually your wheels, right? Yes? Okay, so you got all this happening. So the question would be, if this moves down, right, at the instant it's at the bottom of its stroke, how fast is a particular gear in here rotating at that instant? I mean, there's a lot of things connected to each other, right? I mean, there's a lot of geometry involved in this. If you look at a piston from the side, and you got the crankshaft, at some point it's over here, and then another moment it's over here. So if I move this down, you know, this is rotating around, then a small movement here at the bottom of the cylinder will have a different effect than up here because of the geometry. So you want to know at instants and times how things are related to each other. I know that seems maybe a little bit too far out there, maybe, I don't know. But any two quantities that we can relate to each other, I tell you how much this moves by at an instant, I can tell you what everything else does. All right.
So this is kind of like radar guns that police use in involved calculus?
Well, a radar gun, the way radar guns work is they give you an average speed, right? But the way the laser works, the radar guns, I think it's a laser. They shoot the laser to you, it comes back to them. They measure how much time that took. Then they shoot it again, it comes back to them, they measure how much time that took. And so they know that in an increment of time you moved a certain distance, and that's an average speed, and they know you were going, in that increment of time, your average speed was, let's say, 100 miles per hour. They know you were speeding, right? That's the way they do it. But it's been argued in court that that doesn't work because that's an average speed, and the judges have said, screw you, that still works, because the increment of time was small, right? Look, if I tell you, well, we're going off on a tangent here. You know, if I tell you that an average speed was 100 miles per hour, does that mean that I was going 100 miles per hour the whole time? No, right? So it's been argued in court that, you know, the radar guns, that can't, you know, you can't give me a ticket because that's an average speed. You can't tell me how I was going at an instant in time. And it's just the time increment's so small, they move the point close enough that they can't put it right on top, right? But they move it close enough that they're like, everyone's happy. You're getting the ticket. Slow down.
Everyone's happy except you.
Except you, yeah. Okay.
So it hasn't argued that they can't like
Yeah,
import like a
yeah,
sample.
it won't hold up, yeah. All right, let's try a little bit different problem, all right? Same, we're going to stick with the circle, but I'm going to change the wording of the problem. Let's say a circle is growing such that its area is increasing at a constant rate of 40 square feet per second. When the area, no, let's do it different. When the radius is 4 feet, how fast is the circumference changing? So this problem is very different than the one we had before. In the one we had before, I was pouring paint onto the ground and the circle was growing, right? But I was pouring the paint in such a way that the radius was always increasing by 2 every minute, right? 2 feet every minute. I would have to pour it a particular way for that to happen, wouldn't I? Do you agree? What happens if I pour a bucket? If I just take a bucket and I pour it and it comes out at the same rate, what happens? Initially, it grows really fast, and then doesn't it kind of slow down? Right? That's not a constant radius increase. But if I pour it the right way, I can make that happen. This particular circle is growing so that its area is increasing at a constant rate. So the area keeps going up by the same amount in every increment of time. Exactly 40 square feet per second. Man, that's pretty fast, right? Every second, the area of the circle is increasing by 40 square feet. Exactly when the radius is 4 feet, I want to know how fast the circumference of the circle is changing, which is a totally different quantity, right? But all the setup is still the same. Questions? Everyone's got the problem down? Okay, so what am I going to start with? Some pictures, right? Got a general picture. Got the instant in time. And what I'm given, what I want, and when I want it. Why is this section called related rates? We are trying to find how rates of changes between things are related, right? How is the change in this area of this circle related to the change of its circumference? How can we relate those rates together? All right, general picture. Got a circle, right? It's got a radius. Not much more to that circle. Of course, it has circumference in an area, but that's a general picture of a circle. The instant in time is what? What? The radius is 4, right? 4 feet? That's my instant. All right. James, Justin, Julio, Ryan. I'm going to give you all a 1-point bonus on your next test for having your name tags out like I've asked you. I appreciate that. Let me see here. Justin. Well, you know what? You sign that right there. Hey, it's a bonus, right? Maybe next time. Anyone else have it out there? No? All right. All right, so we'll start over here. Ryan, you want to go? What am I given, Ryan?
You were given
The rate of change
Okay,
of the area.
of the area.
Which is 40 feet squared per second.
Okay, so I'm given a rate of change of 40 feet per square feet, right?
Yes, square feet.
Per second. Ah.
It's dA over dt.
So you want me to write that as dA over dt? Why? Because I need to help everyone else understand why it's dA dt also. Hold on.
Because it's because what we want, or no, because the fit square feet per second, that tells you the dA dt.
Okay, so this right here is telling you that this is a rate, that this is a rate of change. This is a derivative, right? And all you had to do is then tie the quantity, square feet is a measurement of area, to minutes or seconds, which is a measurement of time. So everyone see that? That number is a derivative. All right, moving along, we'll go to the back. What do you want? Anyone there? You want the circumference. Okay, so you want to know how fast?
The rate of change of the circumference.
Okay, so how would you like me to write that?
DC over dt.
dC dt? That's what you want. Everyone agree? You want the rate at which the circumference is changing. You don't want C, right? You're not saying, oh, I want to know what C is. Because no, if the radius is 4, you know what C is. That's not the question. This is related rates. Here, just sign in real quick, Ryan. Okay. All right. When do you want that? When do you want that? When the radius is 4 feet, right? So we have to be a little careful with things like that because, you know, a lot of times we'll say like, we want to know dC dt when it's 4. Well, you have to know what it is, right? Because I could have told you when the radius is 4. I could have told you when the diameter is 10. I could have told you when the area is 80 pi. I could have given you any quantity here, so you need to make sure you know what that letter that goes with it is, right? Okay, now everyone else can sign in. Where are we at? Back table here. What would be the next step?
Finding an equation that has both of them.
Okay, find an equation that has both relate A to C. We've got to relate those rate things together so that we can relate their rates together. Uh-oh. I need to try and find an equation that relates A to C. And unfortunately, we don't have one, right? Not one that we are like very familiar with, right? Yes?
Can you like take the circumference, the area of circumference and solve for r and then plug r into the area, or the area formula?
Exactly. Let's write down the things we do know. That equation won't work for us because it relates A and R. The equation we have for circumference is 2 pi r, right? That relates C and R. But see, there's an intermediate variable there, r, that appears in both. And so if we solve one of these for r, I can take that and plug it back into the other equation for r, and then I've related the A and C together. So I think the easiest one to solve for r would be what? This one right here with the C. So we're going to solve this for C or R? For R. Solve that for R, you get what? R is C over 2 pi. Then take that